Hi, this is Professor Fernandez. This is Class Notes C in Lesson 13. So in this class notes, I want to get you comfortable with this theorem. So let's see what this theorem says. Suppose I have found k eigenvectors of A. K here could be 2, 3, 79, however many eigenvectors you found. And they have distinct eigenvalues lambda 1 through lambda k. Distinct meaning that they're not the same, right? Maybe the eigenvalues are -1 and 7. That would be distinct. If the eigenvalues are -2 and -2, those are not distinct. Those are the same. So suppose I have found eigenvectors with distinct eigenvalues, then this theorem says those eigenvectors are linearly independent. That's very nice. I don't have to check the linear independence condition. I just have to check that the eigenvalues of the eigenvectors are distinct. So that's pretty nice. So in this example, let's see how to use that in practice. So it says, returning to the previous example, are the eigenvectors you found linearly independent? Okay, so I'm just scrolling up a little bit because this is exactly where I put them in the last video. Here are the eigenvalues. Here are the eigenvalues and eigenvectors, I should say, from the previous example. So I'm going to remove some clutter here. So let's employ the theorem. Well, here are the eigenvectors from the previous example. Here are the eigenvalues that they came from. And these eigenvalues are definitely not the same, right? So they are distinct. Again, if there were more eigenvalues, if there were like 5 eigenvalues, you want to make sure, if you want to use this theorem, that those 5 eigenvalues are distinct. No 2 of them are equal. So what is the conclusion here from the theorem? Well, so the eigenvalues are distinct from these 2 eigenvectors. So are they linearly independent? Yes. So I'm going to write, are they Li? Yes. Lambda 1 was -1. Lambda 2 was 2. Okay, and lambda 1 is not equal to lambda 2. Great. Verify your answer using 2 different techniques. So we just verified it using this theorem. What's another way we could verify it? Well, we are now trying to consider a problem that we have lots and lots of strategies for at this point in the course. The problem being showing that these 2 vectors are linearly independent. And part of the reason that I asked the question in this fashion using 2 different techniques, certainly these 2 vectors are not any old 2 vectors. They are eigenvectors corresponding to eigenvalues. So we can use this theorem to verify linear independence, and that's what we just did. Method 2 is, suppose you didn't know that these are eigenvectors. Somebody just, you were walking down the street and somebody stopped you and said, hey, are these 2 vectors linearly independent, right? You would probably think that person is a little weird, doesn't know you, asking you about linearly independent vectors. But you would say, well, I can verify that for you. You've come to the right place. If I put these vectors into a matrix and use them as columns of the matrix, remember we talked in the previous lesson how if I take the determinants, which in this case is 3, and verify this not 0, then indeed the vectors that form the columns of this matrix are linearly independent, right? So that's another quick way to verify that these vectors are linearly independent without having to know that they're eigenvectors or the eigenvalues they came from, and without having to remember this theorem. So that's a second way. A third way would be the usual linear independence definition, right? So we won't do that here. Just wanted to remind you of that condition. All right, so now let's look at part B. So I'm reading here up here, part B. Do the eigenvectors found in the example form a basis for R2? Okay, interesting question. Now we're upping the game, so to speak. Now it's not just about checking linear independence, but we want to figure out if they form a basis. All right, so remember, to be a basis, you have to be linearly independent, and you have to also span. Linearly independent and span R2. We have just shown that these vectors are linearly independent. So all that would be left to do is to show that they span. And then for there, we have 2 different ways to do that, right? So number 1 is we could take an arbitrary vector in R2, and we could try to figure out if it can be written as a linear combination of these 2 eigenvectors. it turns out that this will work, right? But the second condition goes back to a theorem we had discussed in a previous lesson notes. We know that R2 has dimension equal to 2. We also have just shown that these two vectors, the two vectors, v1 and v2, are Li, linearly independent. So in other words, we have found two vectors that are linearly independent in a two-dimensional vector space. So we can go back to that theorem. I believe it's in lesson 12 or 11. We can go back to that theorem and invoke it, and that will imply that v1 and v2 are, that's a span R2. V1, v2 span R2, which implies basis for R2. Okay, so I'm just going to stop there because that's the easiest way to do this. There's really no need to run through the system of equations here that would be required to solve for C1 and C2 if we can just invoke this theorem. So the takeaway from this example is that number one, it could be very easy to verify that eigenvectors are linearly independent. I say could be because if the eigenvalues they came from are distinct, then you just invoke this theorem and you get that result fairly easily. It is also interesting that eigenvectors can form bases for R2 or for other spaces. It's interesting because eigenvectors are of course associated with a matrix A. So as I point out later, this is a little window into this possibility that perhaps a matrix can generate a basis for other vector spaces, right? Certainly, we've talked a lot about the vector space of matrices, the vector space of vectors, but this is kind of teasing this idea that maybe if you take a matrix, its eigenvectors can generate a basis for other spaces. So that's pretty interesting. Okay, so that's the takeaway from this example.